This video is to introduce the topic of thermal physics. And congratulations, in this unit, you shouldn't see sine, cosine, or theta. At least I'm 90% sure of that. So thermal physics is the introduction to thermal energy, which is a topic that's both covered in chemistry and in physics. And so far, we've been looking at systems at what we call the macroscopic level. Macroscopic means large scale, so like the Golden Gate Bridge. We're going to, in thermal physics, look at a system at the microscopic level, incredibly small scale. So this would be like the steel that makes up the Golden Gate Bridge, and we're going to analyze the atoms inside of that metal. Don't write this down because you have this equation already in your notebooks. If we assume that we have a frictionless closed system, the law of conservation of mechanical energy is just your initial potential energy plus your initial kinetic energy will equal your final kinetic energy plus your initial potential energy. However, that's for a frictionless system and a closed system. I've modified that equation for this unit where I've got the same potential and kinetic initial energies. However, now we're going to include in there the work done by friction. So the work done by friction in a system has to be accounted for as well, because some of that potential and kinetic energy is going to be converted to friction, and that friction is going to be adding thermal heat to the system. So here's a little demonstration that you can do for yourself. Pause the video and do this. Rub your hands together for 10 to 15 seconds. Describe to yourself what is occurring in terms of friction and transfer of heat. Think about it in terms of one hand doing work on the other hand and vice versa, and then what's happening to the kinetic potential and thermal energies. So coming back, we're going to define the increase of friction in a system as thermal energy. And thermal energy is defined as the energy that comes from heat. The definition of heat, which is different from temperature, which I'm going to say a number of times, the definition for heat is the energy transferred between objects because of the difference in their temperature, not the temperature itself. So heat is not the temperature of an object. Heat is the transfer of energy because two objects have different temperatures. That's a real important clarification to make, because one of the biggest misconceptions is that the temperature of something describes the heat that that object has, and that is not true. The temperature is just a measure of the object's internal energy. So you may have talked about how we take temperature in the metric system before. However, if you have not, this is the 2 SI units for temperature. First is the Celsius. Celsius named after the astronomer Andres Celsius. And basically the Celsius is based upon the boiling point and freezing point of water. So water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. So that is going to be the temperature range for the Celsius, and that's what the temperature in Celsius is based upon. Makes a lot more sense than the Fahrenheit, and the Fahrenheit, which is based upon the boiling and freezing point of mercury. Well, we have a lot more mercury than we have water, so we like the freezing point of water better. And then we've got the Kelvin. Kelvins are used to gauge the temperature related to the amount of kinetic energy contained in a substance's particles. So think about particles as atoms, and that they are always in motion unless you reach the temperature of 0 kelvins. You can have a no lower temperature than 0 kelvins, because at 0 kelvins, all particles stop moving. The lowest temperature that you can have is 0 kelvins, which if we relate that to Celsius, it's negative 273 degrees Celsius. Important thing to know is when we're talking about internal energy, we're talking about the movement of the particles and those particles' potential and kinetic energies. So temperature is used in kelvins. Here's a question that I'd like you to pause the video and think about. You have 8 milliliters of water at 100 degrees Celsius and 8 milliliters of water at 50 degrees Celsius. When you mix the samples of water, what will be the final temperature, and how did you figure this out? And then the main question here is, when you mix the two samples together, did the hot water transfer heat to the cool water, or did the cool water cool down the hot water? There will be a prompt on Schoology that's a discussion page where you can write your response to this question. Please pause the video at this point and think about your response and type your response to part B. Okay, so for part A, when you mix those two samples of water together, what will the final temperature be? Notice that I have the same volumes of both the hot and the cold water. So the total volume of water is 16, and half of it's hot water, half of it's cold water. So really in this case, all I have to do is average those two temperatures together to get the final temperature of the water when they're mixed. So I say 100 degrees Celsius plus 50 degrees Celsius divided by 2 is 75 degrees Celsius. However, if I had more hot water than cold water, the final temperature would be warmer. And if I had more cold water than hot water, the final temperature would be colder, by the proportion that we added the waters together. For part B, did the hot water heat up the cool water, or did the cool water cool down the hot water? We're going to look at the next slide to see what happens. So when heat is transferred from one object to another, heat will always flow from the one with the most internal energy to the one with the least internal energy. So let's say I have two blocks here. Block A is hotter than block B. This means that the particles in block A are moving around and have more kinetic energy than the particles in block B. Because the particles in block A have more kinetic energy, that energy is going to flow from block A to block B. So when those blocks touch, you go from red to blue, and then when we reach a system of equilibrium, the energies have transferred all throughout the system, and then the two blocks added together have the same temperature. Once we have, in a closed system, the heat transfer has stopped, meaning the whole entire system is the same temperature, we call this thermal equilibrium. In a closed system, the law of conservation of energy is still obeyed, because the heat lost by A is going to be exactly the amount of heat gained by B in a closed system. Here's a demonstration I'd like you to perform at home. Perform it at home instead of school, because the hot water in our sinks does not get hot. Would like you to fill up one container with hot tap water. Make sure it's not hot enough to burn you. Fill another container with cool water. Put your hand in the hot water first. Describe the flow of heat that is occurring, and then describe the temperatures of your hand in the water. And then you're going to remove your hand from the hot water and place your hand in the cold water. And then I want you to again describe the flow of heat that is occurring and describe the temperatures of both your hands in the water. Again, there is a prompt on Schoology. This is going to be discussion question number 2. You can type your responses on that particular page. Pause now, perform the experiment if you're at home, and then go to Schoology, the discussion page, and enter this in for prompt number 2. So since matter is made up of atoms, and atoms never stop moving unless you're at 0 kelvins, which is also called absolute zero, all objects have some amount of internal energy. Internal energy is defined as the amount of potential and kinetic energies that are existing between particles in an object. So we are going to look at a quick animation here, which is going to show what we mean by internal energy. And before we do that, please know that when heat is transferred from one object to another, you are going to change the internal energy of the first object by transferring energy to the second object. All right, so what you're looking at here is a little animation that's going to show the change in internal energy as I go through the 3 phases of matter. So you probably saw this before in physical science in the 8th grade or 9th grade. You might have talked about it a little bit in biology. Here's a solid. Here's your microscopic view of that solid. Take a look at the particles that are in a solid. We can now describe what's going on with those particles in terms of energy. Those particles are packed really closely together and not moving all that much. Therefore, those particles are not exhibiting a large amount of kinetic energy. They are exhibiting a large amount of potential energy. Because they are vibrating, they almost are so packed into place, they're waiting to release their kinetic energy to somewhere else. That's what the internal energy looks like for a solid. With a liquid, now I'm decreasing some of the particles' potential energy, and I'm increasing some of the particles' kinetic energy. Notice not all of them, because a lot of them are still packed pretty closely together, but enough are moving that I've actually changed the phase of matter. Last but not least, a gas. Gases contain mostly kinetic energy and very, very, very little potential energy. That's because those particles are zooming all over the place. So we can say a gas has the most kinetic, the least potential, and a solid has the most potential, least kinetic, inside of the substance. And remember, all of these refer to the internal energy inside of a substance. So I promised I was going to say this again, and here I am saying it again. Heat is not the same thing as the temperature of an object. Heat is the measure of the energy transferred between 2 objects, and those 2 objects are different temperatures themselves, or have different amounts of internal energy. Heat is a measure of energy transfer, so the heat's unit is the joule in SI units, and we know the unit for heat in the standard measurement units of calorie, which we dealt with in the power lab. And temperature is a measurement of that internal energy, and we use the SI units Celsius or kelvins. I did not add or kelvins here, but make sure you know it's kelvins as well. Quick chart to write down regarding variables and the units that measure internal energy and heat. So we call this heat in physics. However, in chemistry, you are going to start using the term enthalpy. Enthalpy and heat transfer are the same exact thing. They call it heat in physics, they call it enthalpy in chemistry. So in physics, heat has a capital Q, whereas in chemistry, heat has a change in H, which it's kind of backwards because they call heat enthalpy in chemistry, but then the variable for enthalpy is H. A little bit confusing. The units, again, because it's energy transfer, is the SI unit joule or non-SI unit calorie. The variable for internal energy is capital U, basically because they ran out of other letters. And we talk about that in joules as well, or calories, because again, it's talking about the internal energy inside of a substance. So here's another situation to think about. So suppose you hammer a nail into a block of wood. Then you pry the nail out of the block of wood with the back of the hammer. When you feel the nail feels warm to the touch. This is going to be prompt number 3. I said 2, but I mean 3. On your Schoology discussion page. I'd like you to describe the energy transfer from the wood to the nail to your hand in terms of work, kinetic energy, and internal energy. So you're going from the wood to the nail, and then from your nail to your hand. So pause this video, think about the energy transfer in terms of work, kinetic energy, and internal energy, and then answer this on Schoology. So here is the law of conservation of energy revisited, and this is an equation you should write down. So another way to state the law of conservation of energy is that the change in potential energy plus the change in kinetic energy plus the change in internal energy is equal to 0. And that's because you can't create nor destroy matter or energy. Therefore, the change of all those things added together has to equal 0. So this is the exact same equation that we talked about in the last unit. We just set the whole entire equation equal to 0. Here is an example problem using that equation. A 0.10 kilogram ball falls 10 meters onto a hard floor and then bounces back up to 9 meters. How much of the ball's mechanical energy is transformed into internal energy of the ball to the floor? I'm going to draw a diagram of this scenario. The ball is going to be dropped initially from a height of 10 meters. The ball is going to go down, and then the ball is going to bounce back up to a height of 9 meters. So somewhere in between hitting the floor and bouncing back up, the floor gained some thermal energy, gained some internal energy, or there was some friction that was gained by the floor. So using this equation, I'm going to rearrange this equation to isolate the change in internal energy. Then I'm going to spell out what delta PE and delta KE mean. not going to spell out what the change in internal energy means because there's no way of me knowing how much energy was in the floor to start with. So I'm just going to call it negative delta U. Negative because I subtracted both sides, delta U. So my final potential energy is going to be the mass of the ball times gravity times my second height. My initial potential energy is going to be mass times gravity times my initial height. Both of these terms, kinetic energy final and kinetic energy initial, are both going to be 0. And those are both going to be 0 because before I drop the ball is not moving. When the ball bounces after its first bounce to a height of 9 meters, the ball is temporarily not moving. So both those values are 0, which makes it nice and easy. So then what I'm going to have here is I'm going to have 0.1 times 9.8 times 9, 9.0 minus 0.1 times 9.8 times 10 equals negative delta U. When I solve all of that out, I get negative 0.98 joules equals negative delta U. So the floor gained 0.98 joules of internal energy in the form of thermal energy. So if we had a thermometer, we would find that the floor got slightly warmer when the ball hit the floor and bounced back up, which is the reason the ball did not return back up to its original height. You're going to practice more of these problems, and the practice is on page 311, numbers 1 through 4, 1 through 5. 1 through 4 are computational questions. 1 through 5 are conceptual questions, kind of like the discussion questions you answered on Schoology. Scroll back through this video, highlight notes that are important, especially the last equation. Also make sure that you've answered your 3 Schoology questions on the discussion page, and we will review this on Monday. Have a good weekend.